So now let us see how to generate and display bootstrap samples from a given data set using Python. So let me just comment that first, generate bootstrap samples. So for this, first of all, we are going to import your NumPy as NP. This is the necessary library that we need. Now let us consider a sample data set. So for this, let me write data np.array. So basically we are creating a NumPy array with the name data, and here we are going to enter the data points. So let that be suppose 23, 28, 32, on 37 we can take, then let us take 44, 49, 55, 61, so 70, and one more we can take. So that makes, so 3 observations, 3, 6, 7, 8, 9, 10. So 10 observations we have taken, and this is an array that we have created. This is the original data set. Okay, now from here we have to generate bootstrap samples. So for this, let me set the random seed np.random.seed as suppose 42. So basically it will ensure that same data or same sample is generated every time I run the code. Now let me write a function to generate a bootstrap sample. So let me first define a function, define generate underscore bootstrap. This is the name of the function, and here I can write data because this is what we want to work with. Okay, it takes data as the input. Now here what we want a random sample np.random.choice, and here what do we mention? From this data set we want to take samples of size length of the data set, like we want each sample should be of size 10 only, and replace equal to true. So it means that we want to do it with replacement. Okay, so it will randomly sample points from this array that we have given. Okay, and it will be done with replacement. So it means same observation can appear twice in your, or maybe more than that, in your bootstrap sample. So the function finally will return the sample that we have obtained. Now let us write for, suppose you want to generate 5 bootstrap samples, generate 5 bootstrap samples. So this is above here. First of all, we have defined a function. Okay, so now every time I am going to call this function generate bootstrap, it will perform these steps and it will return the sample to me. So here let me mention that. So bootstrap samples is equal to, so here I would write the name of this function, or I can take this. Okay, data for I in range 5. So here we are going to generate 5 bootstrap samples. So I have specified the range as 5. Okay, and each sample would be stored in this list that we have created. Now if you want to print this, so let us give that command, print. First of all, let us print the original data as well as the bootstrap sample. So original data. So here we would write this, and if we want all the bootstrap samples, because we need a for loop for that, for I sample in enumerate from these bootstrap samples. Okay, so here we have initiated a for loop and we have used enumerate for this, because in enumerate when we are using this, it will give you both the index also for the sample. Okay, so like it will give you that first sample is this, second sample. So that is why every time we have iterated it, and it will get updated every time. Okay, it will start from 1 and it will get updated. So let us see what it prints. So you can see that you have your original data set, and from here we have generated 5 bootstrap samples from this same data set. Okay, so the values might be repeated. So you can see that 70 and maybe 32 you can see, like in the 4th sample you get 32 twice. Okay, so likewise you might find any other case also. So this is how you can find the bootstrap samples from a given data set. Okay, so now this was the basic idea for the bootstrap. Now let us try to use it in hypothesis testing. How do we incorporate that? In hypothesis testing, let us first consider that we are interested for testing single mean. Okay, so test for single mean. We are first of all going to import numpy as np, and let us consider a sample data set. So maybe we can consider the same thing here that we have defined. Okay, now test for single means that it implies we have the null hypothesis as that mu equal to mu naught, and the alternative would be that mu is not equal to mu naught. So basically we deal with the two-tailed test. And if you can recall the theory, so there we said that first of all we will get the observed data, and from there we are going to find out the sample mean of the observed data. So let us first of all obtain that. So observed mean, let me write observed mean. How will we calculate? We will use numpy's mean function. So we can easily write this, and we also need mu naught because we are testing it against some hypothesized mean. So let that be hypothesized mean. Let us consider that to be 50. Suppose you can change it depending upon the claim that you want to test. Okay, now at this step what we do, we find out the t statistic. So that is basically the difference between the observed mean and the hypothesized mean, right? It was x bar minus mu naught. So this is your mu naught, basically hypothesized mean. So you can calculate your observed statistic here only. Observed statistic. So that would be observed mean, that is x bar, minus your hypothesized mean. So it is the difference between the observed mean, that is x bar, minus mu naught. Okay, so you have calculated t now. Now the next thing that you have to do is you have to generate n bootstrap samples from the observed sample, right? So from this data set now you have to generate bootstrap samples. So what do we do here? We first of all specify what is going to be my n. So let that be like 1000 bootstrap samples we want. Now we write a function to generate a single bootstrap sample, right? We can reuse that single bootstrap sample and compute ti, t underscore I. So let me mention a comment over here that this is basically your t equal to x bar minus mu naught. So I'm just writing whatever we had in the theory. Okay, so here this is the comment. Okay, so mu naught is your hypothesized mean and observed mean. Now we are writing a function to generate single bootstrap sample and compute ti's. So for that, let us define this function, generate bootstrap sample. So let me comment here data and with the observed mean. Okay, so basically what we do is, now initially we had this sample, right, and we calculated the sample mean here. Now the bootstrap samples that will be drawn will be from here, but with this mean, from the observed mean. Okay, so note this change over here, and now we want to find out take out the samples, np.random.choice, and here I would write data. Size would be the length of this sample, length of the data, and replace is equal to true. Fine. So basically we are trying to take a random sample from this data set, not a random sample, in fact we are going to take a bootstrap sample from this data set of size this, and replace is equal to true. It means that we are going to do sampling with replacement. Now in addition, what it will do is it will take the sample and then it will calculate its mean also, np.mean, and here we write sample, and finally what it will return is sample mean minus your hypothesized mean that we have defined earlier. Okay, so this is how we define the function to generate bootstrap sample and compute TI. So this is what is returning is what this test statistic, that is TI that I have written. It is basically sample mean, so xi bar minus mu naught. Okay, so it will return the difference between the bootstrap sample mean and the hypothesized mean, and we want this for n such like 1000 number of times we want this to be repeated. So we will generate that and we will initiate a for loop for that. Generate n bootstrap statistics TI that we want, right? So in order to do that, what we will do, let us use bootstrap statistic. So here I have written observed statistic, that is used for T, and now we are going to find out bootstrap statistic, that is TI. Okay, so this is basically, we will write this function generate bootstrap sample with observed mean. Okay, data observed mean for in range n. So what this will do, this is basically for finding out your TIs, right? So from T1 to T1000 you will obtain this. Now we are ready to find out the p-value. For p-value, what do we need? We need to find I. So basically we have to compare the absolute value of this with the bootstrap statistic, and we have to see for how many times the absolute value basically of observed statistic will be less than the absolute value of the bootstrap statistic, because then only the indicator function will take the value 1, otherwise it will be 0. And for p-value, finally we divide this sum by n. So basically we are looking at the proportion over there. So let me just mention this. So p-value over here is np dot mean. We want absolute value, so ABS I can write. So here I have bootstrap statistic. Is greater than equal to the absolute value of your observed. Okay, so it has compared these two quantities, their absolute values, and then it has taken the mean basically. So basically p-value over here, it is the proportion of the bootstrap statistic that are at least as extreme as the observed statistic. Okay, so this is what we are doing over here. Now once you have obtained your p-value, you are almost done. We will just set the alpha value, so let that be 0.05. And when we have the hypothesis testing, so if p-value is less than equal to alpha, what do? We reject the null hypothesis. We are going to print reject H0, else it will print fail to reject. So now let us print what we have obtained till now. So first of all, let us write what is the observed mean. This is the first thing that we calculated. Observed mean. Next is your print. We can print your hypothesized mean. So hypothesized mean is 50, that we already have. Okay, we can print the p-value, I guess, because that is more needed. So print p-value would be p_value. So you fail to reject the null hypothesis, and you can see that your observed mean is actually 47.7 and your hypothesized mean was basically 50, and if alpha is 0.05, so you can be immediately seen that p-value is greater than alpha, so you fail to reject the null hypothesis. Okay, so it means that if you fail to reject, it means that the population mean is same as 50, right? Mu is equal to 50. We do not have sufficient evidence to reject the null hypothesis. So this is how you can do for mean. This is for single mean. The same thing can be done for single variance also. So the difference, if you can see from here, the difference would come at certain steps, like wherever you are finding observed mean or your hypothesized mean. In all those cases it will come. So let me just show you how it is done. Now for test for variance, we can again import the library, import numpy as np. Okay, now we will also enter the data set. So maybe we can take a different data this time. So np.array. Okay, so this data variable over here, that is data, is holding the sample data set. Okay, this is your numpy's array function. So here we can consider, suppose 21 is there, 28, maybe 32, 37, 30, 22. We can also take 39. So these are just random values. You want to change it, you can do that. 25. This is just to explain you how you should proceed with your bootstrap sampling whenever you are trying to incorporate bootstrap in your hypothesis testing. Okay, so I believe there are 10 values, 6, 9, 10. Yeah. Now what you have to do, first of all, we need observed variance, hypothesized variance, right? And then we can calculate your observed statistic. So let us write that observed variance. So that will be np dot where, because it is a sample variance. So with the name data, and we will also write ddf as 1. This is your observed variance. Okay, sigma square, basically. Not sigma square, it would be sample variance, so that is basically s square. Now we need hypothesized variance. Hypothesized variance. So let us consider that as 50 only. Now once this is there, so you have sample variance and you have hypothesized variance, so you can find the observed statistic, that is t. So observed statistic is basically the difference between these two, observed underscore variance minus hypothesized variance. Fine. So this is hash, I'm just commenting, this is t. Okay. Now what you have to do, you have to generate bootstrap samples. So for that, let us define a function. First of all, define generate bootstrap. So maybe here we can write data, comma, your observed variance, and here first of all we need the sample, so we can use np.random.choice from this data set, and we need the size to be the same as the length of this data set. and it is with replacement. Okay, now sample variance, what will be the sample variance here? We can use numpy's function. So here it would be sample and DDOF is 1, so it specifies it as a sample variance. Now what it will return? It will be returning the sample variance minus your hypothesized variance, right? Because for each TI you need the difference between the corresponding, like for T1, if you have to calculate the T1 statistic, it means you need S1 square minus sigma naught square. So for S1 square, it means that it's a sample variance that we have just now written, right? Minus your hypothesized variance that we already have mentioned over here. Okay, now if you have to generate, suppose n such bootstrap samples, so now let me just mention I want 1000, and maybe I will just copy it from here. So bootstrap statistic will be here, the same command that we have. We are going to call this function, and here we would write data and observed variance for I going from 1 to 1000. Okay, and the p-value would again be, you will be comparing your TI. So let me just comment over here, sorry, these are TIs. Okay, TIs. Here you have obtained T and these are TIs. So now we are calculating the difference between the absolute value of the bootstrap statistic and your observed. Okay, and the average of that, because we are interested in the proportion. So this will basically give you the p-value. If alpha is this, we can again probably reuse these steps over here. Okay, so if p-value is less than alpha, we are going to reject the null hypothesis, otherwise we fail to reject. And here let us see what is the observed variance. So for that we need to write this input statement. Okay, yeah, so we fail to reject the null hypothesis. Observed variance is 43.6 and p-value is 0.727. Okay, so let us try to see what happens if I take 30 as the variance. Okay, so this p-value has decreased now. So observed variance is 43.6. Obviously, if you change these, ultimately you would get, like, variance is suppose 10. So you can see that it is getting affected. So it's 0.389. So obviously you can make it smaller, and if you change these values, at some point you are going to reject the null hypothesis because your p-value would become smaller than your alpha. Okay, so this is how you can do the hypothesis testing for bootstrap samples. Here the idea behind this, as I have discussed earlier also, so here we do not know anything about the distribution from which the data is coming, but still we are able to make decisions, or we are able to check the claims that have been made about the population mean or population variances, right? So this shows the efficiency of your bootstrap concept. So this is for single mean and single variance.